So already we have seen the data path, and we have seen the control signals. So we need the logic that can produce these control signals. So here is the data path. Okay, so I'm showing it at the high level here, the data path. So once we have fetched the instruction from the instruction memory, we have the instruction at the output. So you can see here the instruction is available here at the output of the instruction memory. It consists of 32 bits. So we have the upper 6 bits of the instruction will be the opcode. So we need to examine the opcode. So the main control is going to examine the 6-bit opcode field, and then it's going to output the main control signals. So it's going to output register destination, register write, the extender operation, the ALU source, memory read, memory write, and write back data. Okay, so these are control signals, main control signals, according to our data path that we have developed in the previous lectures, that we have seen in previous lectures. So the input will be the opcode, the output will be these control signals. So these are called the main control signals, which are used by the data path. Some of these control signals are used by multiplexers. For example, in the case of register destination, okay, it's used to control a multiplexer to specify what is the destination register, either RT or RD. ALU source, for example, it's used by a multiplexer, which is going to select the second input to the ALU. Either it's going to be the value on bus B, the output of the register file, or it's going to be the immediate constant. Some of these control signals are going to control the reading, the writing of the data memory, and so on. Okay, so I'll talk about more of, so we have already seen these control signals. So this is the output of the main control. In addition, we need the ALU control. The ALU control is going to receive as inputs the opcode and the function code. So in addition to the opcode, we need the function code. Because in the case of R-type instructions, we have also a function code, and the output will be the ALU operation. The ALU is going to produce the 0 flag. We need the 0 flag. Okay, in the case of branch instructions, branch if equal, branch not equal. So the 0 flag is going to indicate whether the branch is taken or not taken. And finally, what we need is the PC control. So the PC control, the input will be the 6-bit opcode and the 0 flag. Notice that these are inputs to the PC control. And the output of the PC control is the PC source control signal. This control signal is going to control this multiplexer at the input of the PC. So we're going to select, okay, what should be the value of the PC in the next clock cycle? Should we increment the PC, advance the PC just to point to the next instruction memory? Or should we jump or branch? So we can select the jump target address or the branch target address. So this is controlled by the PC control. Now, all of these control, which is shown here in red, are pure combinational circuits. So these are just gates that will receive input and produce output. So there is no memory inside these control logic. Okay, do you have any question about this? Is this clear? Please raise your hand if you have any question. If you would like to ask questions about this topic, just raise your hand, or you can interrupt me at any point in time. تفضل Khalid.
Yes, Doctor. Last time you said that this is not efficient design, right?
This, I said what? Can you remind me? Can you say it again?
It is very slow. Have very slow performance.
Okay. So yes. So what I said is that although this is a simple design, it is this single cycle processor is slow. So I will be talking about performance. This will be my next topic. I will talk about performance and why this is slow and how we can improve the performance of the single cycle design. We're going to look at other designs to make it much more efficient. Okay. Does this answer your question, Khalid? Is this the question?
Do we need to redesign the, for example, the register file, or
I'll talk about how we can. Okay, when we reach this lecture, I will show you how we can do some improvements to this design to reduce the clock cycle and use a faster clock. Yeah, so there are many things can be done to improve the design of the CPU. We can redesign it to make it a lot more efficient. So let us keep this discussion until later. But at least we have a CPU, we have data path, we have control. But before I finish this lecture, I need to talk about the control. So now here we have the single cycle data path, and we are going to extract from the instruction the 6-bit opcode. So notice that the 6-bit opcode is taken from the instruction itself. And this is the main control. It's going to output many control signals. These are called the main control signals. Notice that this register destination, it's used by the multiplexer that's going to select RT or RD, okay, as the destination register. We have register write that is going to enable the or disable the writing of the register file. I have the extender up, which is used by the extender for a sign or zero extension. We have ALU source, which is going to control the multiplexer at the second input of the ALU. We have memory read, we have memory write. These are going to control the reading or the writing of the data memory. And finally, we have write back here data that's going to control this multiplexer, which is going to select either the ALU result or the data at the output of the data memory, okay, that should be written back to the register file in the case of a load instruction. So these are the main control signals which are used by the data path, and we need to generate these control signals. This is the importance of the main control. For the ALU, we need ALU control that is going to examine, so it has to receive two inputs, the opcode and the function code. So both of these are inputs, okay, to the ALU control. The output will be the ALU operation. So the ALU control is just for the purpose of generating the ALU operation, which is needed by the ALU. Now the ALU itself is going to produce a control signal, okay, which is the zero flag. So only the zero flag is being produced here because we're using a very simple design. Just we have two branch instructions that are going to be implemented, branch if equal, branch not equal. We might need other flags, okay, on a real CPU, like for example, if you would like to detect overflow, or if you would like to have to detect the sign of the result, and if it is negative or not, okay, in the case of branch less than 0. Then in this case, we need other flags as well. But here only the 0 flag is going to be used. And we need the PC control. The PC control is going to use the opcode. Notice that the opcode here, in the case of a branch instruction or a jump instruction, we need the opcode, and I need the 0 flag. And the output will be the PC source, which is going to control the multiplexer at the input of the PC. So this is my single cycle data path and control. It's very simple, as I said. Okay, it's very easy to understand. This is my complete CPU. It's a very simple CPU, but at least we have a CPU design here. Okay. The main control signals, we have seen 7. So the first one is called register destination. So let us remember what are their names and what are their effects. So the first one is the register destination. It's going to control the multiplexer here at the that will select the destination register. So the effect when it is 0, we select the destination to be RT. When it is 1, we select the destination to be RD. In the case of register write, the effect when it is 0, no register is written. Okay, in the case of 1, so only 2 values, either 0 or 1. So 1 means that, okay, either the destination register RT or RD is going to be written, and the data will be available on bus W. Data will be on bus W if we enable the writing of the register file. So that's the register write. It's going to enable or disable the writing of the register file. We have the extender op. This extender op is used to control the extender. So 0 means that we use 0 extension, whereas 1 means that we are using sign extension. This is the meaning of these control signals. ALU source, this is going to control the second input to the ALU. So in the case of 0, it means that we are going to select the value of register RT. This is going to appear on bus B. This will be my second ALU input. 1 means that we are going to select the extended 16-bit immediate. This will be my second ALU input. In the case of an immediate type ALU instruction, I need the 16-bit immediate to be my second ALU input. In the case of memory read, okay, so in the case of it is 0, nothing is read, okay, from the data memory. In the case of 1, we read the data memory and we take the output here. So therefore we use the address to address the data memory, and therefore we get the data, the output of the data memory in the case of a load instruction. Memory write, this is going to control the writing of the data memory. So 0, it means that it is not written. 1 means that we are going to write the data memory. So we use the address and the data in. So we have the data input, okay, for the data memory, and therefore this is the data that is going to be written inside the data memory at the specified address, as shown here in this slide. So notice that here the value on bus B, this is my data in. The output of the ALU, this is my address, okay, to the data memory, as we have seen in the previous lecture. So we use the address, okay, so in the case of a store instruction, we need to store the data, the value of register RT, which is available on bus B. This is my input data. This is going to be stored inside the data memory at the specified address. We use the ALU for address calculation. So the ALU is going to compute the memory address. And this last control signal here, which is write back data, if this is 0, it means that we select, okay, the ALU result. This will be available on bus W. In the case of 1, we select the data at the output of the data memory. This will be available on bus W. Okay? So this is the meaning of the control. These are the main control signals, and these are their effect when they are 0 or 1. Now, how do we implement this? We can just draw a truth table. Okay, so we need a truth table for these main control signals. Remember that the input here is the opcode for the main control logic, and we have different opcodes. So we have, for example, opcode 0 for R type. We have a unique opcode for add immediate, set less than, and or XOR immediate. So notice that for register destination, 1 means RD, 0 means RT. Of course, we have to enable the writing. Register write will be equal to 1 for all of these instructions because we are going to write. Okay, so either we write the destination register RD or we write RT in the case of an immediate type ALU instruction. For the extender op, notice that for R type, there is no immediate. So therefore, we don't really care about the extender op. For the immediate type, we use 1, it means sign extension, or we use 0 in the case of 0 extension. That's how we control the extending the immediate constant. The ALU source, 0 means it is bus B, the value on bus B. That is in the case of R type instruction. 1 means the immediate constant. So therefore, we are going to select the immediate constant as my second ALU input. Notice that memory read and memory write are both 0 and 0. Okay, so that's the case when we are not reading, we are not writing the data memory. And we select the ALU result. So that's 0 in the case of write back data. We select the ALU result, okay, to write back the ALU result back to the register file. Okay, so these are the main control signals. Notice that in the case of load and store, in the case of load W and store W, load means that we need to write register RT. Okay, of course, we have to enable a register write. We use sign extension for the immediate. We select the ALU source to be the immediate constant because we are going to do address calculation. Notice that memory read is equal to 1. Okay, that's in the case of a load instruction, and memory write will be equal to 0. And notice that write back data is from the data memory, so it's 1. That's for controlling the last multiplexer. So always keep in mind the image of the data path and the control signals. Remember these control signals, then you will recognize what are their values. Okay. Now notice that in the case of a store instruction, okay, notice that the register write equal to 0 because nothing is written in the register file. We are going to write the data memory. So notice that memory write equal to 1. This memory write equal to 1 because we are going to write the data memory. We use sign extension for the immediate. We select the immediate here as my second ALU source. And we do address calculation in the ALU. So memory read equal to 0, memory write equal to 1. Nothing is written back into the register file. So therefore, I don't really care about the register destination. And I don't really care about write back data. Notice that in the case of branch instructions, branch if equal, branch not equal, the immediate is sign extended. Okay, because it can be signed, it can be positive or negative. Notice that the ALU source is equal to 0, indicating that it is bus B. Why? Because we need to read 2 registers, okay, from the register file, and therefore my second ALU input is the value on bus B. So we need to compare the value of register RS with the value of register RT. So this is why we need to have the second ALU source as the value of register RT on bus B. Okay, we don't read or write the data memory. Notice that these are 0, 0. So 1 here in the case of memory read, it is 1 only in the case of a load. And memory write is only 1 in the case of a store. Notice that nothing is written, okay, by branch instructions into the register file. So register write, nothing is written. So we are disabling the writing of the register file. So this is 0, and this is 0 in the case of a branch. And we don't really care about the register destination because nothing is written. And we don't really care about write back data because nothing is written into the register file. Finally, in the case of a jump, okay, the jump does not really read or write any register. It only modifies the program counter. So again, register write equal to 0, memory read equal to 0, memory write equal to 0, and all the remaining control signals are don't read. So this is the truth table of the main control logic. So we need the truth table. Once we have the truth table, what's the next step? If I have the truth table, what's the next step? Students?
Build the logic.
Design.
I need a logic, right?
Yes.
So how do you implement this truth table? Did you learn this?
Logical gates.
Okay,
Logic
so we
gates.
can use actually gates, right, to implement this. This is a combinational circuit, right? It's a pure combinational logic. The input is the opcode, and we have 7 outputs. Okay, so how are we going to implement this main control logic? Any idea? Any suggestion? واضح انه انتم نايمين، ما نكون صاحيين، واضح انكم نايمين. I don't know if you are present or not. يعني حتى probably بتسجلوا الحضور وبتروحوا بتناموا يعني ولا موجودين ولا مش موجودين؟
Yes, doctor, we are with you.
Yes, doctor.
طيب, okay. So I ask you a question. How are you going to implement this main control logic? Are you going to use the Carnot map and produce gates, or are you going to implement it differently?
Carnot is very hard because we have many input and output. It's not only two or
So
three.
how many input variables do I have here? The opcode consists of how many bits?
7 in our case.
No, the opcode is 6 bits. In the case of the MEMS architecture, the opcode is only 6 bits. Okay, so you have like 6 variables, right? 6 bits means 6 variables. In the case of the Carnot map, yes, the Carnot map, we don't really need the Carnot map. We can actually implement it differently. So can you suggest something for the implementation? Can you suggest something for the implementation? There is an easy way of implementing this logic.
No idea.
Like, can you say, I cannot hear you. Can you raise your voice?
I said no idea. I have
no idea. Okay. طيب, شوف, if nobody has designed this CPU before and you are the first person to actually implement something like this, as an engineer, can you come up with a solution? Yani, let me tell you something. What engineers do, okay, they come up with solutions. They don't memorize solutions and write them in the exam. They come up with the new problems and find solutions for them. This is a true engineer, okay? And the one who is actually just studying for the exam to get a good grade in the course and so on, he's not an engineer. So if you would like to become actually really an engineer, you have to be able to think about solutions to problems, even if you have never actually seen this solution before. Can you do this? Based on the background that you have studied in the 202 course, can you actually come up with a simple way to produce this truth table, the outputs of the control, the main control logic? Is it that difficult? Is it that difficult to produce these outputs? Do I need to explain it to you, or can you figure it out on your own?
Using multiplexers.
Are you trying to use your mind ولا ما في? Is this working? Well, it's not working. Is your brain working?
No idea.
Again, I need to hear from you.
Looks like you need to explain it.
You cannot? طيب. Remember the decoder? What is the decoder?
The output will be 1 at the index of the, for example, if the input is 5, then all the bit output will be zeros except the bit number 5.
Hello. Okay, good. So now I give you a hint. Okay, let us use a decoder to implement this logic. So the input to the decoder will be the opcode. And since we have here 6 bits for the opcode, we need 64 outputs. 2 to the power 6 equal to 64, which are numbered from 0 to 63. You agree? Now, if I would like to actually implement the complete instruction set with all the possible opcodes, I need this decoder. So the inputs will be 6 bits, the output will be 2 to the power 6, 64 possible outputs. Now, how can I output register destination? Using what? I'm going to use a decoder plus extra gates. What are these extra gates? If I would like to implement any Boolean function, okay, how do I implement it with a decoder?
AND gate.
No, we use if you have at most one of the outputs. So in the case of the decoder, one of the outputs is equal to 1, and all the other outputs are zeros, right? As Khalid mentioned. So what do I need? What type of gates to produce? So we can focus on the ones. In this case, we have only
and not.
We can use either OR gates okay, to output the minterms, okay, from the truth table, the ones, you can focus on the ones or you can focus on the zeros. So in the case of register destination, there is only a single one. Notice that the don't cares, which are shown below, you have the choice to make them zeros or ones to simplify the logic. So in the case of register destination can be just R type. So whenever we have an R type, the decoder is going to output 1. So when the opcode equal to 0, then output 0 of the decoder will be equal to 1. And this will be my register destination because it's only equal to 1 only in one case, and it is zeros everywhere. And these don't cares can also be made zeros. So look at the column and look on how many ones and zeros we have in the column. If you have less number of ones, then in this case, you can focus on implementing the ones. Okay, if you have, for example, 2 ones or 3 ones, you can use an OR gate to OR them. If you have fewer number of zeros, you can use a NOR gate. So let us take a look here at the implementation of this truth table. It's really that simple, it's not really that hard at all. So I'm going to use a decoder. Okay, so here the opcode is 6 bits. I need a decoder. Now the decoder will have one output for each opcode. This is really the idea of using the decoder, is that to simplify the implementation. Now we don't really need to have 64 outputs. I need only to focus on the instructions that I would like to implement. So I'm going to have one output for R type. So here when the opcode equal to 0, the R type output will be equal to 1. When the opcode is equal to add immediate, I'm going to have the output here add immediate will be 1. So one of these outputs will be 1, and all the other outputs will be zeros depending on the opcode. So I only have these instructions. Okay, I don't really want to implement the entire instruction set. I only want to implement these instructions. So I don't really need to have an output for every possible opcode in binary. I'm going to only use these opcodes, and that's it. Notice that here I have an opcode for branch if equal, branch not equal, jump. Okay, so all of these are my possible opcodes. I'm going to focus on only these. Okay, hello. So now we have register destination. Let us take a look here at the first output. Now, register destination is going to be equal to 1 only when we have an R-type instruction, according to this truth table. Okay, let me again use here my pen tool. So it is 1 only in one case when you have an R-type instruction. It is 0 otherwise. And these don't cares can be made zeros. You have the flexibility, the freedom to choose the don't care to be either 0 or 1. So I'm going to select these don't cares to be zeros. And therefore, whenever I have an R-type instruction, then RD will be equal to 1. So we don't even need a gate. I just connected with a wire. You can see that here, whenever the output here is R-type, then register destination will be equal to R-type. So that's my output here, register destination. Is it that easy? It is so easy. Omar. Yes, Omar.
So,
yes.
According to the project document, there are some operations that have the same opcode, 51, I believe. Will that
then
make
in this case you have to use the function code. You have to use the function code. Now, for these instructions that have the same opcode, they will have different function codes. So the opcode will not be enough. You have to use the opcode and the function code. But here we are distinguishing between the ALU operation and the main control signals. So even though there are many different function codes for the same opcode, the main control signals are identical the same. Yani, for example, if you have any R-type ALU instruction, whether it's addition or subtraction or a shift or a logic operation, the main control signals are the same. So it does not depend on the function code. It only depends on the opcode. So this is part of designing the instruction set, is that to simplify the implementation. And therefore, you can see that these main control signals do not depend on the function code. So regardless of the function code, okay, the values of these main control signals are the same. Now, when we come to the ALU operation, It depends, of course, on the function code. So I'll come back to this in a separate logic, which is the ALU control. Right. So that's for register destination. Let us take a look at register write. Now, if you look at register write, you can look here at the second column. Notice that we have many ones and you have fewer zeros. Okay. So if I would like to use here, again, my, let me just use here my mouse. I can see what is, just 1 second. Yeah. So here for register destination, notice that we have all of these ones and we have these 4 zeros. So you can look inside the column. Okay, how many ones do you have and how many zeros you have? So we have what, 7 ones or we have 4 zeros. So there are 2 ways to implement this. Either we can use a 7 input OR gate, or we can use a 4 input NOR gate. A 4 input NOR gate will have a lower cost than a 7 input OR gate. So you can output the ones or you can output the zeros. The zeros here means NOR, not OR. Whereas the ones, you can just use a 7 input OR gate. So you have 2 choices, okay? And therefore, we're going to use here a 7 input, sorry, we're going to use a 4 input NOR gate. So we can write the equation like it is shown here. This is a NOR, it's not OR, okay? So whenever we have store, branch is equal, branch not equal, or a jump, so we use here not OR, that will be a NOR gate. So there must be here a 4 input NOR gate that will output register write. This is my register write control signal. It will be the output of a 4 input NOR gate. Okay, so that's basically how we are implementing it. In the case of the extender op, you can see that we have 3 zeros here. Again, we can use a 3 input NOR gate. It is sign extension. Sometimes you don't care, so we can use the don't cares as ones. And therefore, we can just implement the 3 zeros here by using a 3 input NOR gate. So again, here it is a 3 input NOR gate. So see how actually it becomes easy to implement this directly from the truth table. So once we have the truth table, we can implement these equations very easily. So a decoder plus a few gates here to implement the logic equations. Notice that in the case of ALU source, okay, ALU source, we have many ones, we have only fewer zeros, so we can focus on implementing the zeros here. Okay, so 0 here means bus B. So this is in the case of R type. Here we have in the case of branching. Okay, so these are the 3 zeros, so we can actually focus on implementing the zeros. In the case of memory read, it's only just a single one. In the case of memory write, only in the case of store. Okay. In the case of write back data, it's only a single one here. So these don't cares can be made zeros. So this will be actually very easy to implement. Okay, so notice that in the case of ALU source, I'm using a 3 input NOR gate. That's ALU source. This is a 3 input NOR gate. Memory read, you don't even need a gate. It is just load W. Memory write, it is just store W, and write back data is just load W. So this is what you are going to supposed to do in the project, is that you have to figure out these equations. So now you know how to implement these equations using just the decoder. And you can, now you don't need actually a large decoder, you can actually reduce the size of the decoder because you only need to output these outputs depending on the value of the opcode. So you don't really have to look at every possible value of the opcode. You only need actually to look at these values of the opcode. So this can reduce the size of the decoder. We are not really implementing here the full instruction set. If you would like to add more instructions, more opcodes, of course, you need to extend this decoder, okay, to generate outputs for these opcodes. Okay. Fine. Concerning the ALU control, okay, we are going to produce the ALU operation. So let me go back to my highlighter because I cannot see even my pen tool. I don't even see my mouse. Let me check. Yeah, this is actually my highlighter. So we have the opcode and we have the function code. So in the case of R type, we have to look at the function, either AND or XOR. Notice that here we have set less than. We have to implement all of these functions. In the case of R type ALU instruction. In the case of the immediate type, there is no function. Add immediate, set less than immediate. So therefore, there is no function here. So I'm putting it don't care because the function itself is not defined in the case of the immediate type instructions. For all the remaining opcodes, there is no function code. The ALU operation is going to specify what to do inside the ALU. So in the case of AND, we do ending. In the case of addition, we do addition. In the case of set less than, we do set less than. In the case of add immediate, we also do addition. In the case of set less than immediate, we also do set less than, and so on. In the case of load and store, we need to do addition. Okay, why? Because we need to do address calculation. Okay, so this is why it's addition. In the case of branching, we need to do subtraction because we need to compare the values of two registers RS and RT. In the case of a jump, we don't even care about the ALU operation. So now we can actually count what are the ALU operations that we need to support inside the ALU. So we have here, we have AND or XOR, we have add, subtract, and that's it for our instruction set. So we only need actually few ALU operations. We can, of course, extend them if we would like to support like shift instructions, other instructions. We might also support more ALU operations if you want. So you can assign a code in binary for each one of these ALU operations. Yani, for example, let us say for AND, you might assign this code. For OR, you might assign a different unique code. I'm using here a 4-bit coding. In fact, a 3-bit coding will be sufficient because I only have few operations. If you count the number of operations here, let us say AND or XOR, and we have add and subtract, we only have 5 unique opcodes. Okay, we have 5 unique, sorry, not opcodes, operations. We have 5 unique ALU operations that need to be supported. So you need 3 bits. With 5, you need actually 3 bits. Notice that I'm assigning here 4-bit coding in case if you would like to extend to add more ALU operations like shift left, shift right arithmetic. If you would like to provide, for example, in addition to set less than, you would like to support set less than unsigned. So it all depends on what you would like to support inside the ALU. So if you exceed more than 8 operations, okay, you need a 4-bit coding. So I'm choosing this coding here randomly, but you can, of course, select it differently. So what we are defining here the ALU operation in binary. Okay, that's the coding here of the ALU operation. This coding here is not unique. You can define it differently. You can define it according to the opcode or the function code to simplify the implementation. So what you have to do is that you have to derive this 4-bit coding, okay, from the opcode and the function code. And as I said, you can actually come up with a different coding depending, of course, on how you implement the ALU. So the way that you implement the ALU, you define the ALU operation inside the ALU in binary. You can specify these codes. And then the idea is to simplify the implementation of the ALU control. So there is no unique way of defining this 4-bit coding. You can choose it any way that you want. The point is that we have to generate this 4-bit ALU operation in binary, and we have to use it by the ALU. So I'm keeping it here as 4 bits, okay, even though the most significant bit here is always 0, okay. You can actually reduce it to 3 bits, in fact, in this example. I don't need actually a 4-bit coding. 3 bits will be sufficient. So you see that in design, there is no unique implementation. You can actually think about different designs, different way to implement. I'm just explaining actually one way to control the ALU. Right. Also have the PC control. So in the case of the PC control, we have 2 inputs. We have the opcode and we have the 0 flag. These are my inputs to the PC control. In the case of an R-type instruction, Notice that R type here, there is no jumping, there is no branching. So I'm going just to increment the PC. So the output here is the PC source. So 0 means that we increment the PC, 1 means we jump, 2 means that we branch. Okay, of course, this is when the branch is taken. In the case of the jump, I don't really care about the 0 flag. Notice that in the case of R type and the jump, we don't care about the 0 flag. Okay, because in the case of the jump, we always jump. So we select 1, which is the jump target address. Okay, in the case of a branching, we have a branch if equal, we have a branch not equal. These are the 2 possible opcodes. But in the case of a branch if equal, there are 2 cases. Either the 0 flag equal to 0 or 1. Now, if the 0 flag is equal to 1, it means that they are equal. Okay, so we use the subtraction, we use the ALU operation, as we have seen in the previous slide, is a subtraction. In the case of branching, we subtract. Okay, so for this reason here, okay, we have to check the 0 flag. And if the 0 flag equal to 1, it means that the operands are equal. So we select 2, which is the branch target address. If the 0 flag equal to 0, it means that they are not equal. And therefore, we do not branch. So therefore, we simply select 0, which is incrementing the PC. So there are 2 possible outcomes for a branch. Okay, either the branch is taken or the branch is not taken. So in the case of a branch if equal, okay, the branch will be taken if the 0 flag is equal to 1. And therefore, we select PC source to be equal to 2, which is the branch target address. In the case of branch not equal, again, it can be taken or not taken. Okay, it is taken if they are not equal. So therefore, if the 0 flag equal to 0, it means it is taken. And therefore, we use 2. We select 2, which is the branch target address. Otherwise, we increment the PC. Now, if you have any other instruction here, which is other than jump or a branch, we know this from the opcode. We don't care about the 0 flag. And for example, if I had add immediate or end immediate or set less than immediate, then in this case, we simply increment the PC. We don't really need to branch or jump. So this is the truth table of the PC control. So always we come up with a truth table because the truth table is going to define, okay, the logic itself. Now, what is actually left is just to implement, okay, the PC control. That's very easy to implement, really. You don't even need Carnot maps or anything like that. Okay, you just can write the equations, and then you can actually implement these equations. Now, this is the PC control. I'm going to use a decoder. Now, this decoder is going to output only 3 possible outputs. Either we have a branch if equal, branch not equal, or we have a jump. So these are the 3 outputs. In fact, even if the opcode here is 6 bits, you don't even need to have actually for the other opcodes, I don't need actually outputs here. All what I care about are these 3 outputs, whether the opcode is a branch equal or a branch not equal or a jump. Now, how do you know this? You know it from the opcode, the 6-bit binary opcode. Okay, so you can actually look at the opcode and you can use an AND gate. Some of the inputs will be inverted, some of them will not. And based on the opcode, you can just produce, okay, just 1 output for a branch equal, another output for a branch not equal, and a 3rd one for jump, based on the opcode itself. Okay. Now, once we have these 3 outputs of the decoder, what I need to do is that I need to implement the logic. Now, the logic can be described from this truth table. Okay, so notice that in the case of R type or other than jump or a branch, notice that the PC source is equal to 0. In the case of a jump, we say that 1. Okay, so PC source must be equal to 1. And in the case of branching, either it is 0 or 2, based on whether the branch is taken or not taken. I can write an if statement. If the opcode equal to 0, if the opcode equal to jump, then in this case, PC source is equal to 1. It means that we are going to use the jump target address. Else, if it is opcode equal to branch if equal and the 0 flag is equal to 1, then the branch is taken. Or we have the opcode is equal to branch not equal and 0 equal to the 0. So the 0 flag equal to 0. So here the branch is also taken. So it is branch not equal and it is not equal. So therefore, we have to take the branch. Then in this case, the PC source is equal to 2. Else, it means that we are not jumping, we are not branching, then in this case, PC source is equal to 0. So this is a way to describe, okay, the PC control logic with an if statement And we can also describe the equations. Okay, we can write the equations very easily. So in the case of a branching, we branch if we have branch if equal and the zero flag equal to 1, or we have a branch not equal and not 0. So notice that here it is not 0. Okay, so these are the two possible cases in which we have a taken branch. In the case of jump, it means that, so notice that here jump is based on the J output of the decoder. So if you have a jump instruction based on the opcode, so this jump will be 1 only when the opcode is equal to jump. And here a branch is based on this equation here. So now we have three cases. Either we have no jump, we have no branch. So this will be 0, 0. Then in this case, if a branch equal to 0 and jump equal to 0, then we are going to select PC source equal to 0. So we have three possible outcomes. Either there is no branch, there is no jump, then we get 0, 0. Or we have no branch, but it is jump, then PC source is equal to 1. That's when we are jumping. Or we have a branch, but not a jump, then in this case, we have PC source is equal to 2. Okay, so these are actually the three possible selections of PC source. 0 means that there is no jump, there is no branch. 1 means that there is a jump. 2 means that there is a branch. Notice that there is no 3 here because there is no jumping and branching at the same time. Either we are going to branch or we are going to jump. So in the case of the jump, we select the jump target address. In the case of the branch, we use the branch target address. Okay. So that's my PC control. So in summary here, we have seen 5 steps to design a processor. We analyze the instruction set, and this will give me the requirements. And then we select the data path components. Here we have already done this. And we establish a clocking methodology. We assemble the data path from the components, meeting the requirements of the instructions. And then we analyze the implementation of each instruction. So when we do this analysis, we determine the control signals. Okay, so that's what we have done. So we look at the instructions and we analyze them. And then we can see, okay, I need this control signal to be 0. I need this control signal to be equal to 1. And basically, we can define the truth table, okay, for all the control signals. And then once you have defined the truth table for the main control, for the ALU control, for the PC control, you can assemble the control logic. You don't need Carnot maps here to assemble the control logic. You can use decoders. And the decoder actually with some simple logic can actually easily produce for you. Because the nice thing about the decoder is that it will tell you, okay, you will have one output for each opcode. And therefore, you know, if this output equal to 1, it means that this is the opcode. If it's 0, it means it's not this opcode, it's a different opcode. So it's very simple, okay? Using decoders and plus few extra logic, you can really assemble the control logic very easily. Now, MIPS actually makes control easier because the instructions are of the same size. We have seen that all the instructions are 32 bits or 4 bytes in length, and the source registers are always in the same place. Notice that in the immediate type and the R type, RS and RT are exactly the same fields in both the formats. Okay, the immediate constant is always 16 bits. It's always in the same place. The operations are always on registers and immediates, and this actually simplifies their implementation. Okay, so that's it about this presentation. Okay, so I finished here the single cycle data path. Okay, and next time, inshallah, I'm going to talk about the performance, okay, of the single cycle data path. I'll talk about performance in general, okay, how we can measure the performance of the CPU. And I'll talk about a different way of implementing the CPU using the multi-cycle implementation. Okay, so we look at variations of this data path. And then eventually I will be talking about pipelining.